All right, so we know what the limit is now. We've looked at limits from the graph. As I mentioned in the warm-up, the limit then becomes a very important piece of the formal definition then for a function's continuity at a point. So here it is. This one is super duper important. Super, super duper, okay? Maybe super duper duper. Two dupers or two supers, I'm not sure. But you're going to want to memorize it. Is it still frozen? There we go. Okay. So this is called the definition of a function's continuity at a point, and it's a three-step definition. Okay, real quickly, before we look at it, let's think of a function as being a road. The graph is the road, and the function value at x equals c is kind of like where there's a chasm or some kind of canyon or something. A function is going to be continuous if you can come in on the road on the left. We'll call this the road that comes in on the left. If it's connected to this blue thing, which we'll call the bridge, which is then connected to the road on the right. So if a function is continuous at a point, it's analogous to you being able to safely drive across this point on the graph called x equals c. And what three things do you need in order to drive across? Well, first of all, you need a road on the left and right, and you need a bridge. But you can have roads and bridges that aren't in the same spot. So once you have a road on either side and a bridge in the middle, you need them to be at the exact same place. That is, the y value of the road on the left needs to be equal to the y value of the bridge in the middle, which needs to equal the y value of the road on the right. If any one of those three things goes to a different y value, or any one of those things fails to exist, you're not driving across, are you? And therefore, the function will not be continuous there. So this is a nice analogy that helps you remember it. Road, bridge, road. That's what you want. Road, bridge, road. So here's the three-step definition of continuity. A function f is said to be continuous at a point, call it x equals c, if and only if the limit as x approaches c from the left equals f of c, which equals the limit as x goes to c on the right. The limit from the left is the road coming in from the left. It has to equal f of c, which is the bridge, which equals the limit as x goes to c from the right. That's the road going out. Road, bridge, road. And we have a notation for everything now. Before 2.2, we didn't have a notation to decide where the roads were leading at a point, but now we do. Those are the limits. So the limits are the roads. The function value is the bridge. Okay? It's the difference between what's happening as you approach versus what's happening at. We need all three to exist, and we need them all to be the same. So once again, if any one of these three things fails to exist, or any two of them fail to equal each other, you're not driving across. The function will not be continuous there. Okay? Let's try it out. Example 6. Using the three-step definition of continuity, determine whether the function, whose graph is given below, is continuous or not at x equals 0. Show your analysis with correct notation and give a concluding statement. So when we test or quiz over this, I'm going to be expecting you to gather evidence and then make a conclusion and formulate an argument, okay, in a complete sentence. So pay attention to how we do this. We're wanting to determine if this function is continuous at 0. Well, if you just look at the graph, you could tell very quickly that it is or is not continuous at 0. Just by visually inspecting it. It is, right? And you might say it's continuous because you could just drive straight through. Or you might say it's continuous because there's no holes, jumps, or VAs. And you'd be correct. But based upon the three-step definition, we need to write it a little bit more formally. So here we go. We're going to say the limit as x approaches 0 from the left of, what's the function's name? F of x is what? What's the limit from the left of 0? 1, right? And then next I'm going to say f of 0. That's the bridge. What's f of 0? Now you're looking for the dot. It happens to also be at 1. And now the road that exits is really the road that comes in from the right. The limit as x goes to 0 from the right-hand side of f of x. If you follow it in there, boom, it equals 1 as well. So this is the gathering of evidence step. You've checked all three things. And now you write your concluding statement. Since, or because, if you want to write it out, there's more letters in because, since 1 equals 1 equals 1. Now what does that mean? Does 2 equal 2 equal 2? Yes. But by saying 1 equals 1 equals 1, after I've gathered my evidence, I'm basically saying, since the limit from the left equals the function value, which equals the limit from the right, but I'm writing them as 1 equals 1 and equals 1. It's a lot faster to write 1 equals 1 equals 1 than writing all this notation again. But if you have it labeled up above, we know which ones you're talking about. And all three of them have to equal each other. So it's not silly to say 1 equals 1 equals 1, because you're referring to each of those ones up above. So since 1 equals 1 equals 1, comma, f of x is continuous at x equals 0. So let me show you how I would grade this on a quiz. On a quiz, you would get a check for the gathering of each of the three pieces of evidence. Then you would get a check for the justification. The since part is your justification. Since 1 equals 1 equals 1. And then, of course, you're answering the question. Boom. There would be your fifth check. Now, on a test, I would probably make this only worth 2 checks. One for the evidence and one for the other 2. But on a quiz, that's 5 checks. That's pretty darn important. Right? We're checking what the road, bridge, road values are. We're comparing them down here in the since part, and then we're making a statement in a complete sentence. Okay? Now, because of the adverbial clause, since 1 equals 1 equals 1, you can actually put those in either order. You could say f is continuous at x equals 0 since 1 equals 1 equals 1. However you want to do it. Pretty easy, right? All right. So let's look at example 7 now. Given the following graph, determine if the function is continuous or not at the indicated values. All right, so now we're not going to just do it for one thing. At x equals negative 4. Well, if you come over here to negative 4, visually looking at it, you could tell right away it is or is not continuous. It is not continuous. Now, based on a 3-step definition, here's what you are not going to say. You're not going to say that f of x is not continuous at x equals negative 4 because there's a hole there. The hole is actually a consequence of how it is not continuous there, based on the 3-step definition. It's not the reason it's not continuous. It's a consequence of how it's not continuous there. So let's go ahead and gather the evidence. The limit as x goes to negative 4 from the left of f of x is what? What's the limit from the left? 2. What is f of negative 4? Look high, look low. Look high, look low at negative 4. Is there a bridge? There's no bridge. So this is DNE, which means we really don't have to keep going. But I want you to walk through all 3 steps. If we're just testing for continuity, as soon as one of them fails to exist, it's game over. So let's go ahead and find all 3 pieces. The limit from the right of 4 is also 2. So we have 2 roads. And more than that, we have 2 roads that are lining up on either side of the canyon. All we would need to make this graph continuous is to have a bridge right there at negative 4, 2 to connect the 2 roads. And that's why this one is a removable point discontinuity. We can actually redefine removable point discontinuity in terms of a limit. When the limit from the left equals the limit from the right, but that does not equal the function value, whether the function value exists somewhere else or doesn't exist at all, we're going to have a removable point discontinuity. So now we'll say, what? What's our answer? Since f of negative 4 equals DNE, comma, f is not continuous at x equals negative 4. You don't have to say f of x is not. Remember, the name of the function is f. So if this were a quiz, I'd give you a check for gathering each of the 3 pieces of evidence, 1 for your reason, and then 1 for your answer. Your reason, your justification, is the one that follows the since part. And here's how you would do it again. If any one of them fails to exist, that's a good enough reason. Or if any 2 of them do not equal each other, but are finite actual values, that's fair enough, or that's enough right there. Okay? It's only if all three of them do exist and are the same that it is continuous. Now, because the general limit exists, but the function value doesn't, that's why we have a hole there at x equals negative 4. All right, at x equals 1, let's look at x equals 1. We obviously see that there's a jump there. But based upon the three-step definition, that's not going to be a sufficient answer. So let's go ahead and write out the machinery. If you want to get this done first, the limit as x goes to negative 1 from the left of f, f of negative 1, and the limit as x goes to negative 1 from the right. What am I doing here? I'm getting out the three pieces of evidence that I need to find, and I'm writing down the notation. If you don't have the correct notation written down, you're going to lose points. Okay, this is speaking the language. You've got your road, your bridge, and your road. And again, notice on the limit, we define our input underneath the limit, and we leave it as f of x up here. But in the function notation, we actually plug in for x in the function notation what the input is. Road, bridge, road. Get those up and going, and now all you got to do is come back and look at the graph and fill them in. What is the limit from the left of negative 1? I'm sorry, from positive 1. I wrote this as negative 1 each time, and there's a quick way to get them wrong. We're approaching positive 1 from the left, not negative 1. Yeah, it is 4. It is 4. So this is going to be a 4 from the left. What is the function value at 1? Now you look at 1, you look high and low for a piece of the graph, and there's the solid dot right there. See it? That's also 1. That's also 4. Now in this case, you got a road coming in from the left, and it's connected to the bridge. Maybe they were built by the same construction company, right? But then the people that were constructing the other road didn't get the memo where that road was supposed to lead, and the limit from the right goes to negative 2. So here they all three exist. We have a road, a bridge, and the road, but now two of them are not equal. So now you say since 4 does not equal negative 2, f is not continuous at x equals 1. And because the general limits do not equal each other, guess what type of discontinuity we have? A jump. So anytime the limit from the left does not equal the limit from the right, we have a jump. All right, and the last one here at 6, you could tell that it's not continuous. There's another hole, but here's what the notation would be. The limit as x goes to 6 from the left of f, f of 6, and the limit as x goes to 6 from the right-hand side. Again, this is getting your pieces up and running. And now you could just visually inspect. The limit from the left and right are both 5. So the general limit exists, and it's 5. But the road is at 2, or the bridge is at 2. And so now you would say, since 5 doesn't equal 2, f is not continuous at x equals 6. Perfect timing. All right. Have a good day. Retest this tomorrow. Don't forget, I'll be here after school if you have questions.